Alright, so what I want to do today is, before we get into proving spacing results, I wanted to talk a little bit about some of the homework problems, given that there were some issues in terms of how to do the proofs. There also seems to be some lighting issues with this, so I'm going to try moving this a little bit and seeing if that works. Okay. Alright, so for the first problem, there was a lot of confusion into exactly what are you supposed to be trying to prove. So it was, I think, prove if alpha is rational, then n to the k alpha mod 1 is periodic, and 2, if alpha is irrational, then n to the k alpha mod 1 never repeats. So it's very important to look at what you're being asked to prove and prove what you're being asked to prove. So for instance, the second one, it's not saying prove that if alpha is irrational, then n to the k alpha mod 1 is not periodic. It's possible for it to be aperiodic and repeat. So for instance, imagine, so for 2, imagine if n is even, n to the k alpha mod 1 is 0. If n is odd, n to the k alpha mod 1 is, the first time it will be 1/2. Then it'll be 1/4, 1/4. Then 1/3, 1/3, 1/3. Then 1/4, 1/4, 1/4, 1/4, and so on and so on and so on. So here it's going to repeat many, many times, but the sequence itself will never be periodic. So there's lots of different counterexamples and sequences like this that you could work with. So you always want to be careful that you're proving what's asked. Okay, so now for 1, so we know alpha is rational. So let's say alpha equals a over b. Now we want to look at n to the k alpha, which is n to the k a divided by b. So since we're dividing by b, it makes sense to write n as something times b plus a remainder. So we can write n as maybe cb plus r, where 0 less than or equal to r less than b. And now when I look at n to the k a over b, this is going to be cb plus r to the k a over b. When I expand this out, everything is going to have a b except for the r to the k term. And so it's going to, this will equal an integer plus r to the k a over b. And so this proves that it's periodic with period b. So when you look at the values, you get 0, and then r would be 1, you would get a over b mod 1. Then when r equals 2, you would get 2 to the k a over b mod 1, all the way down to b minus 1 to the k a over b mod 1, and then back to 0. So all that matters is the remainder of n when you divide by b. Okay? Okay, so that's the first part.
So,
yep.
the function, the definition of periodicity is just f of a equals f of a plus b?
Basically, to be periodic, there's some period, say t, such that f of x equals f of x plus t, when you differ by a fixed amount. So I don't want to use a and b because we've got a and b right here.
For all x.
For all x. Right. And so you could have a subsequence that's periodic. So for instance, if I looked at this function, if I looked at f of 2n would be periodic because the evens are periodic. The evens, bless you, are just all 0, 0, 0, 0, 0, 0, 0, 0, 0. But because the odds have interesting behavior, and you can play lots of games with something like this, you could have strings of zeros and ones. And so for the second one, we now want to show that if it's irrational, then it never repeats. If it never repeats, could it be periodic? No. So we definitely know that once we prove 2, we know it can't be periodic. But it's possible that just because it's not periodic doesn't mean it doesn't repeat. So we've got to be very careful as to which statement we prove. Okay. So proof of 2. So assume n to the k alpha equals m to the k alpha mod 1. Okay, well, if this is the case, then what this means, it looks like there is a light explosion, and so I'm just trying to see if there's any way to minimize how much light glare there is. It's a little bit better. Okay, so this means there exists an integer a such that n to the k alpha equals m to the k alpha plus a. So then if we subtract, we get n to the k minus m to the k alpha equals a. So alpha equals a over n to the k minus m to the k, which is rational. And by assumption, the denominator is not 0 because we're assuming we have 2 different points. So this is all we need to do to show that it never repeats. So if you notice, this is actually very similar to the proof when k equals 1. Okay, I know one of the other problems was the triangle inequality. Everybody seemed to be good on that one. There was the cosine to the n, and what was the other one?
N factorial e.
N factorial e. Okay, yes. So was the claim to show that it was not equidistributed or not dense?
That it was an integer. Yeah, that was not equidistributed.
Okay, let's show it's not dense.
Showing that something's not dense means that it's not equidistributed.
Correct. So if you show it's not dense, it can't be equidistributed. Right.
But we don't have, dense does not imply equidistributed necessarily.
Dense does not imply equidistributed. So for instance, you could imagine a sequence such that, x2n is, say, n alpha mod 1. Alpha is irrational. And x2n is, I'll choose 7. No, I'll choose 4. 4 7s. If alpha, actually sorry. So we'll do x2n is n alpha mod 1, x2n plus 1 is 4 7s. So this sequence is going to be dense because just this top half is equidistributed, so that will get you density. The bottom half is always 4 7s. If I still take the union, if I take this alternation between the two sequences, it's still going to be dense. It was dense before, I'm just adding in a new value. But it will no longer be equidistributed because now half the mass will be at 4 7s. And this was in honor of the Houston Astros scoring 4 runs and winning Game 7 and eliminating the Yankees. Okay? I love being a professor at times. So if we can show something is not dense, it's not equidistributed. But if we show something is not equidistributed, it's not the same as showing that it isn't dense. So let's look at the problem we have. Proof that n factorial e mod 1 is not dense. Well, e is equal to 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus yada, yada, yada. If we multiply by n factorial, the first terms all the way up to 1 over n factorial become an integer. So we get n factorial e is equal to integer plus 1 over n plus 1. And the next one is plus 1 over n plus 1, n plus 2. The next one is 1 over n plus 1, n plus 2, n plus 3, and so on. Okay? So we have something like this. And when we look at this mod 1, the integer doesn't matter, and we're left with just this quantity here. So a lot of people said, we have a sum of terms tending to 0, therefore it converges to 0. We've got to be careful. 1 over n, the harmonic series, diverges. So you've got to be very careful. It's not enough to have a sequence of terms that tend to 0. They have to tend to 0 fast enough. So what we want to show is that once n is sufficiently large, this sum is small, and it's going to be really close to 0. And so since it's really close to 0, there's no way it can be dense, because there's only finitely many terms in the beginning that can only flutter around so many points, and then all the remaining stuff will be clustered near 0. So we want to get an upper bound for this sum. These are all positive terms. The sum should be really small. Can anybody think of a series that dominates this? I'm sorry? Okay, so you have 1 over n squared. We have a 1 over n plus 1 over here. Right, so if we chop off all the stuff over here, we have a lower bound of just one term. Remember, we're trying to understand this for specific value of n. We want to evaluate this sum. We want to bound 1 over n plus 1 plus 1 over n plus 1, 1 over n plus 2, plus 1 over n plus 1, n plus 2, n plus 3. Like this. Clearly, it's at least 0. But we need an upper bound for that sum. Any thoughts as to how we could get an upper bound for that sum? So do you think the sum converges or diverges? Converges. So we need a series that will dominate this and will converge. What's our go-to series? Geometric. When in doubt, try to see a geometric. What would you choose for the ratio?
1 over n to the r.
So geometric. What do you want r to be? So we're looking at this fixed series here. 1 over n plus 1, plus 1 over n plus 1 times n plus 2, plus 1 over n plus 1 times n plus 2 times n plus 3. I'm sorry?
1 over n plus 1.
1 over n plus 1. This would be less than or equal to r plus r squared.
Yeah.
R squared would be larger than this because we have an n plus 2. So our sum will be less than or equal to r plus r squared plus r cubed, which is equal to r over 1 minus r.
Yeah.
So this is 1 over n plus 1, 1 minus 1 over n plus 1. All right, 1 over 1 minus 1 over n plus 1, this is n plus 1 minus 1, which is n over n plus 1. So I flip it becomes n plus 1 over n. So we get an upper bound of 1 over n, which is nice and clean. So what this is telling us is if we look at this series mod 1, here's 0, here's 1. If you take 1 over 1,000, if you take n equals 1,000, all the terms with n equals 1,000 and higher all lie in here. So you have at most 1,000 values in through here. It can't be dense. You'll have to have gaps in here. Just choose some interval where you don't have any points. Since this works, do I have to do 1 over 1,000? What if I did 1 over 2? What if I take n equals 2? Well, okay, then this is no longer drawn to scale. All right, so here's 1/2. So if I take all the terms with n greater than or equal to 2, all the terms with n greater than or equal to 2 live in here. I have one term that can live in here, the n equals 1 term. Okay? I don't know where it is. Well, actually, I do. What's e? About 2.71828. So if I take e mod 1, 1 times e mod 1, or 1 factorial times e mod 1, it's going to be about 0.71. So this is enough to clearly prove that it's not dense. There's nothing from 0.8 to 1. Okay, so just to recap, it's not enough to say we have a sequence of terms tending to 0. We really need to understand how rapidly they're tending to 0. And what's nice is this series converges extremely rapidly. Now the question is, how big of an assumption, or I'm sorry, how bad of a bound do we get by replacing all of these n plus 2, n plus 3, n plus 4s with n plus 1? Can somebody give me an easy lower bound for this infinite sum? Easy lower bound. It's at least 1 over n plus 1. Using the geometric series bound, we get it's at most 1 over n. Oh, okay, so we're differing between 1 over n plus 1 and 1 over n. If n is large, this is not a big deal. If n is small, yes. I would rather have it as a grade, 1 over 1% versus 1 over 1 plus 2%. Right? 100% is much better than 50%. But if n is a billion, there's really not much of a difference between 1 over a billion and 1 over a billion and 1. And so this is not a bad bound. Okay. Any other questions on this one? All right. The last one was the really interesting one. Right? That was the one where I think we had cosine n to the n, and then trying to show rigorously that this that the sum diverges. Right? So there's a lot of different ways to prove a sum diverges. One of the things I like about this is the difference between a necessary condition and a sufficient condition. And these are often confused. Can somebody give me a necessary condition for a sum to converge? Terms have to go to 0. If the terms don't go to 0, can your sum converge? No. It might stay bounded, it might oscillate, but the sum can't converge. Is that a sufficient condition that the terms go to 0? No, we have the harmonic series, 1 over n. So just because the terms go to 0 doesn't mean the sum converges. But if the terms don't go to 0, it can't. So we're trying to study cosine of n to the n. All we need to do is show that the terms don't go to 0. And then we know it can't converge. So what we want to do is we want to show that the cosine of n is close to 1. Now we measure things in radians. So the cosine of n is never going to be a nice rational multiple of 0, pi, 2 pi, 3 pi, 4 pi. It's never going to be plus or minus 1. The cosine of n is always going to be strictly less than 1 in absolute value. And we're raising it to a huge power. So if you were just a little bit less than 1, when you raise it to an enormous power, hopefully you are enormously less than 1. And so all we need to do is show that the cosine of n is far enough away from 1, or negative 1. Other way around. We want to show that cosine of n is so close to 1 so many times that even when we raise it to the nth power, it's going to still be close to 1. So imagine I have the number e to the negative 1 over square root of n. Is this number, what is this number close to when n is large?
1.
It's close to 1. By Taylor, this is approximately 1 minus 1 over square root of n. The next term would be 1 over 2n, and so on and so on and so on. So when n is very large, it's about 1 minus 1 over root n. If I take e to the minus 1 over square root of n, and I raise this to the nth power, this is e to the negative square root of n. What is that approximately when n is large? So we have e to the negative square root of a googol. So if I put in a very large value of n, what should e to the minus n be? E to the minus square root of n be approximately? This is the same, remember, as 1 over e to the square root of n. This should be very close to 0, right? When n is large, if you want to expand the bottom, it's 1 over 1 plus root n. I mean, this is a really crappy bound. But it would be greater than 1 over the square root of n. So if I take e to the negative 1 over square root of n, those numbers are all less than 1. But they are far enough away from 1 that when I raise it to the nth power, I'm essentially 0. So if those were my terms, would the sum converge or diverge? It would converge. So what you would want to do is you'd want to go a little bit further here, plus n over 2 plus n to the 3 halves over 6 plus n squared over 24. So this would be greater than or equal to 24 over n squared. And then, oh, sorry. It was this way, because I've made the denominator smaller. So this sum would be bounded by the sum of 24 over n squared, which is 24 times pi squared over 6. So if these were my terms, they would converge, even though each one of them is damn close to 1. And as n gets larger and larger and larger, they get closer and closer to 1. What's going on? Even though they're close to 1, they're still far enough away from 1 that when we raise it to the nth power, it's magnified enough that they go down. Can you give me a sequence of numbers that are so close to 1 that when I raise it by the nth power, it's still close to 1? So here, these things were all close to 1, but when I raised it by the nth power, it was very far from 1. I want something now that's close to 1, and when I raise it to the nth power, it's still close to 1. So what should I try now? So what went wrong here? When I raised this to the nth power, I got e to the negative square root of n. Before I had a 1 over square root of n. Now I have an e to the negative square root of n.
N cubed, e to the negative 1 over n.
So if I try e to the negative 1 over n cubed, right, this is going to be approximately 1 minus 1 over n cubed. Is this closer to 1 or further to 1 from this? Much closer, right? This differs from 1 by like 1 over n cubed. This differs from 1 by 1 over square root of n. If I now look at e to the negative 1 over n cubed, it's a terrible division sign, to the nth, this is e to the negative 1 over n squared, and that's approximately 1. So now, if I were to sum this as my series, it would diverge. So the whole point of cosine of n to the n, the only way we're going to show this diverges, or at least a good way to show that this diverges, is to show that we are so close to 1 that when we raise it by the nth power, we are still close to 1. That means, in some sense, we have to be able to approximate a rational multiple of pi or 2 pi really well. Okay? Because if we can approximate that really well, the cosine of 2 pi is 1. And then this would be very, very close to 1. So close that even when we raise it by the nth power, we're close to 1. Okay, so let's try to do the details now. So this was meant to be motivation. So by Dirichlet, we can do 2 pi minus pn over qn less than or equal to 1 over qn for infinitely many n. So we can form a sequence like this. And so we'll have a sequence, pn, qn, distinct, and they're going to infinity. Well, what this means then is 2 pi qn minus pn is less than equal to 1 over qn. I missed the square, thank you. That would be bad. So what this means then is that 2 pi qn equals pn plus theta n over qn, where theta n is less than 1, less than or equal to 1. Because 2 pi is irrational, I could replace all these less than equal to's with less thans. It's fine. So now, the cosine of 2 pi qn equals the cosine of pn plus theta n over qn. Or conversely, the cosine of pn is the cosine of 2 pi qn minus theta n over qn. Which one do you think is the one we should work with? First or the second?
Expand that on.
Yeah, because we're trying to look at the cosine at a special point, at a special integer. So we'll just choose our n's to be, the sequence pn. If I look at this one, this is 1, but now I have to expand using the angle addition formula with the cosine of pn and the cosine of theta n. Ugh, I don't know both. But with this, I know the cosine of 2 pi qn. When I expand that out, I'll get cosine, minus, plus sine.
Sine, right?
Yes. But is it a minus or is it a plus?
I think it's sine a plus b over 2, sine a minus b over 2. And twice. Yeah.
So I will make sure that you guys, I'll leave it to you to check, is it cosine minus or cosine plus? It doesn't really matter because the sine of 2 pi qn is 0. It doesn't matter for us. But you should know if it's a plus sign or minus sign. So this is just equal to the cosine of pn is the cosine of theta n over qn. And theta n over qn is really close to 0. So we now need to just get a sense of how close to 0 is it. Okay. So we now know that the cosine of pn is the cosine of theta n over qn. Well, the best case for us is if theta n is 0. It's not going to happen, but then we would have the cosine of 0, which is 1. Cosine is symmetric, right? So I can actually put in absolute values here. And so now this is going to be, let's just Taylor expand. It's 1 minus absolute value of theta n over qn plus absolute value of theta n squared over, this is squared with a 2. And then this would be to the 4th over 4 factorial qn to the 4th minus theta n to the 6th over 6 factorial qn to the 6th. Okay? So this is just expanding out cosine. Well, when theta n is really, really small, if I truncate here, is what I truncate positive or negative? So say theta n is theta n over qn is a really small positive number. If I truncate my cosine expansion here, do I get an upper bound or a lower bound for the cosine? A lower bound, because all of this stuff here, the net effect is positive. This is a alternating series, right? And the series is, the terms are strictly decreasing. So this, if I truncate it here, I've made it smaller. So we know that the cosine of Pn is greater than or equal to 1 minus theta n squared over 2 factorial Qn squared. Now we should raise both to the pnth power. So cosine of Pn to the Pn is greater than or equal to 1 minus theta n. Actually, I can drop the absolute values because I'm squaring it, over 2 Qn to the Pn. So there's something here that I don't like. What's a little bit annoying? So I'm just raising both now to the pnth power, but do I have a Pn inside here? No, things are in terms of Qn. Sorry, it should be Qn squared. I would love to have this as a Qn, not as a Pn. This is almost looking like an e, like a definition of an e to some value. 1 minus blah over something large to something large. But this is actually the square root of what's over there, so it's a little bit subtle. I'd like to replace the Pn with a Qn. Which is larger, Pn or Qn? Well, approximately what's the relationship between Pn and Qn? So Pn should be larger. 2 pi is a little bit more than 6. So Pn should be larger than Q. Do you think Pn could be 7 times larger than Q? Well, if Pn were more than 7 times larger than Q, then Pn over Qn would be at least 7. And that's a crappy approximation to 2 pi. So once n is large, we know Qn is 7Qn is greater than Pn if n is large. Right? So if I replace this with 7 times, let's see, am I doing this the right way? No, I'm sorry. Pn over Qn is at most 7. Yeah, okay. So 7Qn is greater than or equal to Pn. If I replace Pn with 7Qn, what do I do to this side? Do I make it larger or smaller? I make it smaller. I'm raising it to a higher power. Now, how much am I really changing things? Not really that much. I don't really care about, a factor of 7. If it was close to 1, if it was damn close to 1, if I raise it to the 7th power, it'll still be close to 1. I need this to be going to 0 if it has a chance to converge. If it wasn't going to 0 before, raising it to the 7th power is not going to help it go to 0. So I get the cosine of Pn to the Pn is greater than or equal to 1 minus theta n squared over 2 Qn squared to the 7 Qn. And this is a valid substitution. What you would almost love to do is to then write, Qn over Qn, use the definition of E, and be done. Right? So the danger here is doing limits in the wrong order. So let me just argue incorrectly. We've got some time, so I'm going to deliberately make mistakes. Because it's good to see how delicate these arguments can be. Let's look at 1 minus let's take this limit. 1 minus 1 over n to the n squared, 1 plus 1 over n to the n squared. And let's see what that should be. I can write this maybe as the limit as n goes to infinity, 1 minus 1 over n to the n, and then 1 plus 1 over n to the n to the n. What does 1 minus 1 over n to the n go to? What is 1 minus n? Yeah, this goes to e, not e. Not a good day for minus signs. This goes to e to the negative 1. So this piece here goes to e inverse. Then I raise it to the nth power. So this piece here is looking like e to the minus n. 1 plus 1 over n to the n, what does that go to? That goes to e. I raise that to the nth power. That goes to e to the n. So what should this limit go to? Should just go to 1. So do we agree that this limit is 1? I have done many illegal things here. I have a limit, and what I've done is, okay, I have this limit of this product. I'm going to do it as the product of the limits. That's maybe okay if the limits exist. Oh, wait, this limit's plus infinity. That could be bad. Also, what I'm going to do is I'm going to take the limit of this inside part and just hold this n in strategic reserve, take the limit as n goes to infinity, and then have this swoop in and deal with things. What is the only good way to handle products like this? Take the log, right? Here's a fast way. This problem is deliberately designed. This is the same as the limit as n goes to infinity of 1 minus 1 over n squared to the n squared, if you just multiply. And now that's exactly the definition of 1 over e. I'm just going through the values n squared rather than the values of n. And last I checked, e is not the same as 1. Oh, sorry, this is e inverse. Well, if I multiply by e, then it's still e is not the same as 1. So you have to be very careful when you have limits. The best way to do something like this is to take logarithms. So if we go back to our expression over here, we want to see what this is. If theta of n is 1, we're in great shape. I'm sorry, if theta of n is 0, we're in great shape because it's just 1. The further theta n is from 1, the smaller it could be. So what's the worst case for us? I'm sorry?
Did we take,
So in this expression here, what's the worst case for us for theta of n? What value of theta of n makes this as small as possible?
2q
I'm sorry?
Wait.
Remember, theta n was between negative 1 and 1, right? Because we have a really good rational approximation to 2 pi. So theta of n is between minus 1 and 1. Which value of theta n will make this expression as small as possible? One, right? As theta n gets larger and larger and larger, this expression gets smaller and smaller and smaller. So the worst case for us is when theta n equals 1. So if we continue the argument, it's sufficient to consider the case when theta n equals 1. So worst case is theta n equals 1. And so now we have cosine of Pn to the Pn is greater than or equal to 1 minus 1 over 2 Qn squared to the Qn. At this point, there's several ways to go. The way I think I see a better way than what I did now. We're just trying to show that this doesn't go to 0. Right? We don't have to show that this stays close to 1. It does stay close to 1, but if I want to just prove that it doesn't go to 0, I just need to find a way to bound this from below. So we just replaced theta of n with 1. What could we replace the subtraction with? Now I want to get another lower bound. I have a Qn over here. What would I love to have downstairs? So what does this kind of look like? Yeah, it looks like the definition of E, maybe e to the negative 1/2. But I've got a Qn squared and I have a Qn over here. Instead of a Qn squared, what would I have loved to have here? Yes?
Why did you drop the 7?
By mistake. Thank you. The 7 doesn't really make a difference, but I should keep it. Thank you.
Yeah, if you drop the 7, it's larger than
Yes.
7 QN, so it doesn't go up.
Right. But keeping the 7 here, everything will be fine. So what would I love to replace the Qn squared down below with? Yeah, with 7Qn. Can I do that? Will that make things larger or smaller? So instead of subtracting 1 over 2 Qn squared, I'm going to subtract 1 over 7 Qn. Which is larger, 2 Qn squared or 7 Qn? When n is huge. N is huge. Which is a bigger number to subtract off? 1 over 7 Qn or 1 over 2 Qn squared?
1 over 7 QN.
Yeah, so if I subtract off something more, I'm going to make it smaller. So this will be greater than or equal to 1 minus 1 over 7 Qn to the 7 Qn. And then this converges to 1 over e, which is greater than 0. So the series cannot converge because the terms are bounded above from 0. Okay? What I want to do now, we've got 5 minutes left. I don't want to start a new topic with 5 minutes. I want to just show that these terms tend to 1. What should we do to understand this quantity here? How do we understand a quantity like this? What do we do? Take logs. Right? When in doubt, if you were taking one of my classes, whenever you see a product, whenever you see an exponent, think logarithms. So the log of cosine of Pn to the Pn will be greater than or equal to 7Qn, the log of 1 minus 1 over 2 Qn squared. Well, the log of 1 minus u is minus u squared over 2 minus u cubed over 3. So this is greater than or equal to 7Qn. I'll pull out the negative sign, and we'll have 1 over 2 Qn squared plus 1 over 2 times 2 Qn squared. So now when Qn is really, really large, if I dropped all of these terms over here, I would make this side less negative. So what I can do really is, I'll leave it as an exercise. This is greater than or equal to negative 7 Qn 1 over Qn squared. That the sum of all these terms from here onward is not as large as 1 over 2 Qn squared. So I've now made things more negative. This is a lower bound. 7Qn squared, this is going to be negative 7 over Qn. So now when I exponentiate, if I have the log of cosine of Pn over Pn is greater than or equal to negative 7Qn, then when I exponentiate, I will get the following. Is it tracking? No, it's not tracking. So then we would get, the last bit is the cosine of Pn to the Pn would be greater than or equal to e to the negative 7 over Qn. And what does e to the negative 7 over Qn go to? It goes to 1 because the Qn's go to infinity. So this was a little bit of a weaker statement. It proved that we have a sequence of values, cosine of Pn to the Pn, which is going to be greater than or equal to 1 over e minus epsilon infinitely often. Here's a stronger statement that we can get within epsilon of 1 infinitely often. So the series diverges. So these are really good problems to review your analysis, how you deal with these infinite series. So the question which I asked you to think about is what would happen with sine? If there was an exam for this class, you might be able to guess what an exam question might be, right? Do a similar argument for sine. Maybe it's essentially the same problem. Maybe there's really no difference. And now instead of going around 2 pi, we just go around pi halves. Maybe it's not that big of a deal. The Taylor series expansion of sine is different than the Taylor series expansion of cosine. Does that make a difference? It was really nice that we had 1 minus something squared. And that was giving us a little bit of extra decay here. But we didn't actually need that much decay. We just needed enough to get something that was greater than 0. The other thing is you always want to get a sense of how bad is your approximation. So if you are American Airlines, and I know we did this in operations research, what is your objective as American Airlines? Profit, yes. Keeping my flights constant is definitely not one of their priorities, as my inbox will show. You want to make money. You want to figure out how you should fly planes. Your revenue is hopefully in the billions of dollars. Differences on the order of 10,000 is not going to be noticeable. And it's not worth obsessing about that because you can't even trust results along those lines. You want to get a sense of how bad is this approximation? How bad is it to bound this with that? And so what we saw today is we actually got to see how much of an error are we making. And in all of our worst case scenario, let's say theta of n is 1 because that's going to be the worst for us. And let's drop all these terms and let's combine all these things. And at the end of the day, we got that this was still greater than e to the negative 7 over qn, which is very rapidly tending to 1. So even when we're raising it to a high power, we even increased the exponent possibly, right? It's nice to get a sense of how much security you have. If you have a lot of security, you can afford to be very cavalier in your bounding. And you should always be as careless as you can. And then if it doesn't work out, then you roll up your sleeves and you do it a little bit more carefully. And say, all right, I was obviously too wasteful here. Or I can't really take the limit of part of an expression and then have the other part come in later. Okay, that's not right. But it's sometimes nice to get some sense of what's going on. In that product that diverged, we had one piece that was going to 0 and another piece that was going to infinity. So in that case, 0 times infinity was 1 over e. It was going to infinity just a little bit faster than it was going to 0. So that their product was going to 1 over e. Oh, wait, sorry, maybe the other way around. Okay, this is a good place to stop. Keep working on projects.